Hello everyone. I will explain the high-performance driving from the objective to the principle and theory part 1. In the next videos, I will explain the principle of high-performance driving part 2, the way of dry run, and the individual high-performance driving skills. I have a quiz for you. Which of the following correctly describes the behavior of a vehicle when the handbrake is applied while turning? The weight of the vehicle is shifted to the front wheels. The load on the rear wheels increases. Understeer occurs. The load on the front tires is lightened. High-performance driving is dangerous, so just understand what is explained here and do not actually do it. Understanding what's here will give you a good understanding of the vehicle behavior in a race car. Still, if you want to try high-performance driving, check the following precautions in advance. Make sure there are no obstructions around you. Check if your driver's insurance covers high-performance driving. Avoid high-performance driving in your own vehicle. Wear all safety equipment. Use a vehicle with a reinforced structure for high-performance driving. Disable ABS and ESP or TCS. Don't drive on the public roads. Use a vehicle with a low center of gravity. The road surface must be hard. Use a wet road surface with a low coefficient of friction, a slippery road surface with a little snow, and a flat unpaved road surface with small particles. Avoid roads with high friction coefficients, muddy roads, roads with sand or snow, and uneven roads as there is a risk of rollover. Slide and spin control. Sliding or spinning should not occur on all wheels at the same time. The objective of this video is to help you to understand the principles and theories of high-performance driving, predict the behavior of the vehicle, and cultivate the ability to develop your own high-performance driving skills. The purpose of high-performance driving is to drive on a given road in the fastest and safest way by predicting and controlling the behavior of a vehicle based on the physical principles of vehicle dynamics. Related principles are friction circle, weight transfer, centripetal force, spin and sliding, linear inertia and rotational inertia. And finally, we need some of driving skills. Since there are too many related contents, this video will explain only the principle of friction circle and weight transfer, and the rest of the principle will be explained in the next video. Coordinate system described here uses the right-hand coordinate system for forces and moments and the left-hand coordinate system for steering angle delta and slip angle alpha, as used in the previous video of the brush model. In addition, it is assumed that the vertical load distribution of the vehicle in a stationary or constant speed driving state is the same for the front and rear wheels. The force required for high-performance operation is the friction force generated parallel to the road surface, which includes traction, braking, and lateral force, all of which are determined by multiplying the vertical force by the friction coefficient. The role of vertical forces is therefore very important. The vertical force does not necessarily have to be large, but the vertical force change can be used to perform high-performance driving. For example, if the vertical force of the rear wheel decreases due to braking, the friction of the rear wheel decreases and the steering wheel can be rapidly rotated to slide the rear wheel, and the developed oversteer by that can be used to make a sharp turn or a 180-degree J-turn. As explained in the last video E0060 when you accelerate, the load on the front wheels becomes lighter and the load on the rear wheels becomes heavier. As a result, as a secondary effect, the absolute value of the acceleration force that can be handled decreases at the front wheels and increases at the rear wheels. Conversely, when braking, the load on the front wheels becomes heavier and the load on the rear wheels becomes lighter. Accordingly, as a secondary effect, since the maximum traction force or maximum braking force is the value obtained by multiplying the vertical force by the friction coefficient, the absolute value of the brake force that can be tolerated increases increases in the front wheels and decreases in the rear wheels. The most important factor in understanding the theory of high-performance driving is the principle of the friction circle. In reality, the friction ellipse is the correct expression because the maximum braking force or maximum acceleration force is greater than the maximum lateral force, but for convenience of explanation, the friction circle is used. In the figure, the solid circle represents the maximum friction force and the point O represents the constant speed driving state in which there is no force in any direction. Point A represents the maximum acceleration force of the driving wheels, point B represents the maximum braking force of the brake wheels, point C represents the maximum lateral force during left turning, and point D represents the maximum lateral force during right turning. A point inside the solid line represents the friction force in a specific operating state. For example, point X represents the state of the drive wheel accelerating slowly on a road with gentle cornering, and point Y represents the state of the brake wheel performing relatively large braking on a road with sharp cornering. In order to understand the meaning of the friction circle, let's look at the operating state that the 2 points X and Y mean. The point X on the friction circle represents the driving state of acceleration during left turning. The green vertical component represents the left turning lateral force component, the blue horizontal component represents the traction component, and the red arrow pointing to the X point represents the resultant force. Point Y represents the driving state for braking in a turn. The green vertical component represents lateral force component, the blue horizontal component represents the braking force component, and the red arrow pointing to the Y point represents the resultant force. The principle of the friction circle can be explained by the expression that when driving at a given speed on a road surface with the same friction coefficient, the absolute value of the available maximum friction force is always constant regardless of the combination of acceleration and braking forces and lateral forces. For example, point E represents the maximum friction force as one of the combinations of traction and left turn, and point F represents the maximum friction force as one of the combinations of braking and right turn, and the absolute values of these maximum friction forces are the same. Furthermore, the absolute value of the available maximum friction force represented by an arbitrary pointer is also equal to the absolute value of the maximum friction force at points E and F, and exists on the circumference of the friction circle, and has the same value in all combinations of braking force, traction force, and lateral force. All they represents the radius of the friction circle. The figure here shows the friction ellipse measured in an actual test. As shown in the figure, the test result is in the shape of an ellipse, not a circle. The characteristics of the test results are, firstly, that the maximum absolute value Fx of the acceleration or braking force is greater than the maximum absolute value Fy of the lateral force. Secondly, when a little braking force is added, the lateral force Fy becomes the maximum. The friction circle changes according to the vehicle's speed on the same road condition. As shown in the figure, every size of the friction ellipse represents 0, 50,100,130 per hour, and as the driving speed increases, the friction circle gradually decreases. Therefore, it can be seen that as the speed of the vehicle increases, the maximum usable friction force gradually decreases, and from this, it can be seen that braking, traction, and cornering during high speed are more difficult than at low speed. The friction force becomes 0 due to zero normal load. The friction ellipse becomes a friction point, not a friction circle or a friction ellipse anymore. When the vehicle brakes heavily, all the weight is transferred to the front wheels. Then, the rear wheels come off the ground and the vertical load on the rear wheels becomes 0. When a RWD vehicle accelerates heavily, all of the weight is transferred to the rear wheels, the front wheels come off the ground, and the vertical load on the front wheels becomes zero. In addition, the vertical load becomes zero when the inner wheel is off the ground due to the increased centripetal force during cornering. When the wheel is off the ground, the vertical load becomes zero, so the frictional force of the corresponding wheel becomes zero, so it becomes a friction point that means zero friction force. In the friction point state, all vehicle operations such as steering, braking, and acceleration are impossible. Looking at the relationship between the normal load and the friction circle, since the friction force is the value obtained by multiplying the friction coefficient by the normal load, the larger the normal load, the larger the friction circle. Accordingly, even for the same tire, the size of the friction circle varies depending on the driving condition. For example, taking the right front wheel as an example, the driving state of straight driving at constant speed is 0, and the friction circle at this time is the green circle C. Next, during maximum braking, the normal load increases in the front wheels and the driving state at point B is reached, and the friction circle at this time becomes the red circle B. Also, in the maximum constant speed left cornering, its driving state becomes pointed at the right wheels, and the friction circle at this time is the blue circle A. But the left wheels come off the ground, the normal load is lost, and the frictional force disappears. Therefore, friction circle is reduced to friction point O. In order to find out the friction circle corresponding to the optimum traction and braking force distribution of a 4WD vehicle, we will use the vehicle specifications listed here. These are the same specifications in the last video numbers H0001 and H0007. The length LF from the center of gravity to the front wheel and the length LR to the rear wheel are the same 1.403 m. The height of the center of gravity is 0.436 m, and the weight of the front and rear wheels is the same at 770 kg force. Let's analyze how the friction circles appear on the braking and traction force distribution obtained in the last video. The figure here is a graph of the optimal traction and braking force of the 4WD vehicle described in the last video H0007. The dotted two graphs show on the vertical axis the optimal frictional force required for the front and rear wheel when a vehicle with the same weight distribution on the front and rear wheels accelerates or brakes with the acceleration or deceleration corresponding to the horizontal axis. Please be careful, FXF and FXR are forces applied to one of the front or rear wheels, not to the two front wheels or the two rear wheels. The sum of the two frictional forces results in a total resultant force, resulting in a green dashed straight line. Point O indicates constant speed driving without traction or braking. Point A indicates when the rear wheels come off the road due to braking, and point E indicates when the front wheels come off the road due to traction. When the wheel comes off the road surface, the friction force disappears and becomes zero, and points A and E become friction points, not friction circles. Let's first look at the front wheels. Point O indicates a stationary state or constant speed driving state, and since frictional force is not used, it has a friction circle corresponding to normal load. When braking, the acceleration has a negative value and the weight moves to the front wheels, increasing the vertical load, so it becomes a state of G. At this time, as the weight increases, the radius of the friction circle becomes larger than the point O. On the other hand, when accelerating, the normal load decreases due to the decrease in weight on the front wheel, so it cannot accelerate beyond point D. So point D becomes the maximum acceleration state and the radius of the friction circle becomes smaller than point O because the weight decreases. If you continue to accelerate here, the friction circle gradually decreases, and when you reach point E, the friction force disappears and becomes a friction point because it reaches the tilting acceleration where the front wheels come off the road surface. At the rear wheels, when accelerating from point O, the acceleration has a positive value and the normal load increases as the weight transfers to the rear wheel, resulting in a state of F. At this time, as the weight increases, the radius of the friction circle becomes larger than the point O. On the other hand, when braking, the weight on the rear wheel decreases. That means the normal load decreases, so braking force beyond point B is impossible, so point B becomes the maximum braking state and the radius of the friction circle becomes smaller than point O because the weight is reduced. If braking continues here, the friction circle gradually decreases and when it reaches point A, the friction force disappears and becomes a friction point because it reaches the tilting braking where the rear wheel come off the road surface. Here we have a figure of what has been explained so far. What you need to know additionally is that if the engine power and friction coefficient are sufficient at point F of the rear wheel, acceleration is possible until the front wheel reaches the tilting acceleration state E. However, if the friction coefficient is insufficient, the friction circle becomes small and wheel spin occurs in the rear wheel, making acceleration impossible. Likewise, if the braking torque and friction coefficient of the front wheels are sufficient, braking is possible until the rear wheels reach the tilting braking state A. However, if the friction coefficient is insufficient, the friction circle becomes small and wheel sliding occurs on the front wheel, making braking impossible. Let's look at the friction circle of the front wheels during acceleration of a front-wheel drive vehicle. Circle of the same color in the left and right figures should originally have the same size, but the size of the right circle is smaller than that of the left circle because the screen is small, so please refer to this fact for your understanding. The point O represents the state of stop or constant speed, and becomes the circle O. When accelerating, the weight of the front wheel decreases, so the radius of the friction circle decreases and the traction force increases, so the driving state becomes point H with the friction circle H. If you accelerate to the maximum friction force, the weight decreases larger, so the frictional force used becomes larger than point H, so the operating state becomes point D, but the friction circle decreases and becomes circle D. At point D, the maximum frictional force is used, so the front wheel becomes unstable even with a small lateral force. In addition, when a large driving torque that generates a force greater than the maximum frictional force is applied, the front wheel spin occurs the moment the traction force becomes greater than the friction force. The operating state also becomes a point E less than the point D of the maximum frictional force and exists on the circumference of the friction circle E because the slip gets bigger. As the magnitude of the traction slip increases, the friction circle decreases, and when the magnitude of the slip increases infinitely, the operating state becomes small to the friction circle F. The important thing here is that DEF's driving state uses maximum friction force, so if even a slight lateral force occurs, the front wheel is pushed outward. If spin and lateral sliding occurs in the front wheel, steering is impossible, so be careful. Let's look at the friction circle of the rear wheels when accelerating a front-wheel drive vehicle. When accelerating, the rear wheels are not driven, so no force is applied. Therefore, the operating state is the point O. But, since the vertical load on the rear wheels increases when accelerating, the friction circle at this time becomes a red circle which is greater than the constant speed friction circle shown in green, and all the friction force corresponding to the inside of the red circle can be used. This time, let's look at the friction circle of the rear wheels when braking the rear wheels of a front-wheel drive vehicle. This is equivalent to activating the handbrake connected to the rear wheels. The point O indicates a state of rest or constant speed, and the friction circle corresponding to this is the circle O. When braking by pulling the handbrake lever with half a full stroke, the weight of the rear wheel is reduced, so the radius of the friction circle is reduced to a circle H, and the driving state is point H due to the applied braking force. If the maximum friction force is reached by pulling the handbrake with full stroke, the normal load on the rear wheel is further reduced, so the friction circle becomes a circle D that is smaller than the circle H, and the friction force used becomes a point D that is greater than point H. Here, point D exists on the circumference of the friction circle D because the maximum frictional force is used. If a braking torque produces a braking force greater than the maximum frictional force is applied, the moment the braking force becomes greater than the frictional force, the absolute value of the slip increases and the friction force decreases. The friction circle is reduced from circle D to circle E, and the operating state becomes point E, which exists on the circumference of friction circle E. As the absolute value of the braking slip increases, the friction circle decreases, and when the absolute value of the braking slip becomes 1, the wheels is locked and the global sliding occurs. At this time, the operating state is point F and it exists on the circumference of the friction circle F. The important point here is that DEF's driving state uses maximum frictional force, so if even a slight lateral force is generated, lateral sliding occurs and produces oversteer, and high-performance cornering can be performed using this. Next, let's look at the friction circle of the front wheels when the handbrake is operated, which is connected the rear wheels in a front-wheel drive vehicle. When the handbrake is operated without stepping on the accelerator pedal, the braking force does not act on the front wheels, so the driving state is a point O and the vertical load on the front wheels increases, so the friction circle increases in size as a red circle compared to the green constant speed friction circle. The front wheel can use all the friction force that falls inside the red circle. Let's find out the friction circle of the rear wheel when the rear-wheel drive vehicle accelerates. Unlike the front-wheel drive vehicle, the normal load on the rear wheel increases due to weight transfer when it accelerates, so the friction circle increases as the acceleration increases. Therefore, since a larger friction force can be used compared to front-wheel drive, the vehicle can be accelerated to the tilting acceleration where the front wheels come off the ground if the friction coefficient is large enough, the engine torque is sufficient, and the center of gravity is high. In this case, as the acceleration force increases, the friction circle continues to increase in the order of h, m, and n, reaching the tilting acceleration d. However, if the friction coefficient is not sufficient and the center of gravity is low, spin occurs in the traction force before the tilting acceleration, and further acceleration is impossible. This time, let's look at the case where spin occurs in the rear wheel during acceleration because the friction coefficient is smaller than the value required for the front wheel tilting acceleration. The O point on the rear wheel indicates the state of rest or constant speed, and becomes the circle O. When accelerating, the weight of the rear wheel increases, so the radius of the friction circle increases and the acceleration force increases to a point H. At this time, the friction circle becomes a circle H. If you accelerate to the maximum friction force, the weight increases at rear wheels, so does the friction circle. Therefore, the friction force used becomes greater than point H and the driving state ends up with point D. At this driving state, the friction force is not available due to using the maximum friction force, and the driving state located on the circumference of circle D. Therefore, at point D,
The rear wheel becomes unstable even with a small force in any direction because all the available friction force has been used up.
In addition, when a large driving torque that can generate a force greater than the maximum friction force is applied, the rear wheel slip gets bigger as the force from the engine becomes greater than the friction force. The operating state also becomes the point E less than the point D of the maximum friction force and exists on the circumference of the friction circle E. As the size of the traction slip increases, the friction circle decreases. When the magnitude of the slip increases infinitely, the operating state becomes point F and exists on the circumference of the friction circle F. The important point here is that DEF's driving state uses maximum frictional force, so if even a slight lateral force is generated, lateral sliding occurs in which the rear wheel is pushed outward. At this time, oversteer occurs in the car due to the lateral sliding of the rear wheel, and high-speed cornering can be performed using this. Next, let's look at the friction circle of the front wheels when accelerating a rear-wheel drive vehicle. When accelerating, the front wheels are not driven, so no force is applied. Therefore, the driving state is point O, but since the vertical load on the front wheels decreases when accelerating, the friction circle at this time becomes a blue circle which is smaller than the constant speed friction circle shown in green, and all the friction force corresponding to the inside of the blue circle can be used. A friction circle during handbraking of a rear-wheel drive vehicle is not different from that of a front-wheel drive vehicle, so I will skip that explanation. This figure shows the maximum acceleration of the rear-wheel drive vehicle and the front-wheel drive vehicle in G-unit, or dimensionless acceleration according to the position of the center of gravity. I explained this graph in the last video E0060. The specifications of the vehicle are as shown in the table. Horizontal axis represents a fraction of the distance from the center of gravity to the front wheels divided by the wheelbase. This figure shows the friction limit in the braking and acceleration and also the tilting braking and tilting acceleration of a sample vehicle. This SUV vehicle have the same wheelbase and CG height as those in the previous slide. LF equals LR vertical axis represents the entire friction force produced by all four wheels, and horizontal axis shows the G unit. As you can see here, when the friction coefficient equals 1.1, the front tires use up all the friction force for braking at driving state B and the rear tires use up all the friction force for traction at driving state A. Therefore, when the force due to the braking torque exceeds B, sliding occurs on the front wheels, and when the force caused by the engine torque exceeds A, spin occurs on the rear wheels in the case of the rear-wheel drive vehicle. The absolute values of all of them are less than the forces corresponding to tilting braking and tilting acceleration. As a result, in an ordinary passenger car, when the friction coefficient is 1.1, the acceleration cannot exceed state A and the deceleration cannot exceed state B. All the acceleration and braking should happen between state A and state B. In general passenger cars, the longitudinal CG position of a front-wheel drive vehicle increases starting from 40% of the wheelbase from the front wheels, and that of a rear-wheel drive vehicle decreases starting from 60%, so the center of gravity position of the entire passenger car exists in the range of yellow shading. Since the quantity of G unit of the passenger cars in this range is below the tilting acceleration, when a driving force from the engine torque is greater than the maximum frictional force, rear-wheel spin occurs in a rear-wheel drive vehicle and front-wheel spin occurs in a front-wheel drive vehicle. The size of the friction circle and the location of the driving state depend on the driving condition. When the rear wheel reaches the tilting braking, the rear wheels come off the ground and the rear wheel friction circle becomes the friction point. On the other hand, all the weight is shifted to the front wheels, which increases the friction circle on the front wheels and increases braking friction force. During acceleration, when the front wheels reach the tilting acceleration point, the front wheels come off the ground and the front wheel friction circle becomes the friction point. On the other hand, all the weight is shifted to the rear wheel, which increases the friction circle of the rear wheel and increases traction friction force. When the centripetal force increases during in a right turn, the weight is shifted to the left and the right wheels come off the ground. The friction circle of the right wheels become a friction point. On the other hand, the weight of the left wheel increases, which increases the friction circle and increases the lateral friction force. When the centripetal force increases during the left turn, the weight is shifted to the right and the left wheels come off the ground. The friction circle of the left wheel becomes a friction point. On the other hand, the weight of the right wheel increases, which increases the friction circle and increases the lateral friction force. The driving condition of a wheel attached to the road surface depends on the size of the friction coefficient. Point R is when the applied force is equal to the maximum friction force, and point Q exists in the green friction circle when the applied force does not exceed the frictional force. The friction circle for Q is bigger than that for R because normal load of Q is bigger than that of R. On the other hand, when the force produced by vehicle exceeds the maximum friction force, the driving state becomes P and exists on the circumference of the friction circle.
Let's look at how friction circles are applied in driving through next two examples. By looking at the friction circle, you can see the driving condition of the vehicle and whether it is a front-wheel drive vehicle or rear-wheel drive vehicle. Looking at the figure, since the driving state of the front wheel is on the left turn axis of the friction circle and is smaller than the maximum friction force, the difference friction force FPF from the maximum friction force is an available friction force. Let's define FPF as the available friction force of the front wheel. On the other hand, the rear wheel uses all available friction force for the traction in a left turn. Since we have front wheel without traction and rear wheel with traction, it can be seen that it is a rear-wheel drive vehicle. In this state, if the traction force of the rear wheels even slightly increases, the rear wheels no longer have a frictional force to use, so the rear wheels spin, reducing the friction circle and pushing them to the outside of turning. On the other hand, since the front wheel still has an available frictional force FPF, no spin or sliding occurs. Therefore, oversteer can occur by generating spin on the rear wheel by stepping on the accelerator pedal so that the rear wheels slide outward, while maintaining a frictional force between the front wheel and the ground. Rear-wheel drive vehicles use this technique when cornering. Let's take the second driving example. Looking at the figure here, the driving condition of the front wheels uses all available frictional force while traction in a left turn. Since the driving state of the rear wheel is on the left turn axis of the friction circle and is smaller than the maximum friction force, the difference friction force FPR from the maximum friction force is the available friction force. Here, similarly to the front wheel, let's define FPR as the available friction force of rear wheel. Since we have front wheel with traction and rear wheel without traction, it can be seen that it is a front-wheel drive vehicle. While maintaining the steering angle, if you keep the accelerator pedal and pull the handbrake connected to the rear wheel is locked and sliding occurs. That means the normal load decreases in the rear wheel and the braking force is added so that the rear wheel has no available friction force. Therefore, while the rear wheel sliding occurs, the friction circle is reduced and pushed rear wheels to the outside of turning. On the other hand, in the front wheels, since the acceleration has been reduced as the normal load increases, the friction circle increases, so the available friction force FPF can be secured, so spin or sliding does not occur in the front wheel. Therefore, oversteer can occur by generating sliding on the rear wheels and turning them outward while maintaining frictional force between the front wheels and the ground. Front-wheel drive vehicle use these principle when cornering by left foot braking, not by hand braking. I will explain the left foot braking in the upcoming videos.
Drivers who are good at high-performance driving use the tire friction force as close as possible to the circumference of the friction circle that shows the maximum friction force for either the front wheel, the rear wheel, or the left wheel or the right wheel. There is a risk of failure in using all of the maximum frictional force of the friction circle because spin or sliding may occur even with a small disturbance from the road surface. For example, if drivers A, B, and C drive a vehicle in the driving state indicated by the dots in the figure when the tire has a black friction circle, A is the best driver with the smallest lap time. On the other hand, driver C shows the longest lap time. Let's find out the answer to the quiz. Which of the following correctly describes the behavior of a vehicle when the handbrake is applied while turning? The answer is number 1. The weight of the vehicle is shifted to the front wheels. Here we have summary. Purpose of high-performance driving is to drive on a given road in the fastest and safest way by predicting and controlling the behavior of a vehicle based on the physical principles of vehicle dynamics. I explained first part of principles of high-performance driving. As for the weight transfer, when accelerating, the front wheel load decreases and the rear wheel load increases. When braking, the front wheel load increases and the rear wheel load decreases. As for the friction circle, the maximum friction force of a tire is constant in all directions. The maximum friction force of a tire can be expressed as the vector sum of the maximum longitudinal friction force and the maximum lateral friction force. The friction circle becomes smaller as the driving speed increases and larger as the vehicle slows down. The friction circle increases as the vertical load increases and decreases as it decreases. The driving state in constant speed straight driving is the origin, center, of the friction circle. If you watch the previous videos, you can easily understand upcoming videos. In the previous video E0058, I explained how the relationship between rolling resistance, longitudinal slip and fuel efficiency is induced in a theoretical formula and their meaning on the graphical representation. Recently, in video number H0059, I explained the meaning of the signs and related expressions for practical and theoretical slips.
In the next video, I will explain the second part of principles of high-performance driving. Please hit the thumbs up and catch the brand new videos by free subscription, so what are you waiting for? See you at next videos. Goodbye guys.